Thank you very much. Thank you very much for inviting me here. It's a great pleasure that I'm back in Philadelphia after being here for the first time for ICRA. So today, what I'm going to talk is a line of research about tactile sensing that I've been very interested and really been trying to push over the last few years. And the title of the talk is going to be Perceiving, Understanding, and Interacting through touch. So I want to start by giving you a high-level perspective of why I do what I do. I basically work at the conjunction between machine learning and robotics. And some of the motivation from the machine learning side of things is generally the fact that we've seen in the last few years some pretty impressive advancements from algorithmic perspective on having AI that can now solve tasks that were unthinkable 10 years ago. Things like AlphaGo and Atari, StarCraft more recently. However, most of these problems are in very structured and basically game environments where it's possible to acquire the equivalent of hundreds of years of experience very fast. And one of my basic motivation is, from an algorithm perspective, is how do we scale these AI algorithms to more complex unstructured domains? Domains that can go from logistic and decision making to finance, biological sciences, and specifically the domain that I'm mostly working on these days. So one question I get quite a lot is, why robots? Why are we working on robots? My personal motivation is that I believe that robots can be fundamentally beneficial for our society. And maybe a little bit controversially, I would like robots to be deeply involved with industrial automation. I would like to replace every single kid that works in a coal mine in Vietnam or that is making our shoes somewhere in India. I would like to replace all of these people with robots so that there is really no need for manual job in the 21st century. I also would like robots to be able to be more useful when it comes to disaster relief. In places like Fukushima, where people cannot go because it's, of course, very dangerous, I think that robots can play an important role in being able to help us. And similar things also in exploration, interplanetary exploration over Mars. We already, we have been on the red planets through robots that are there. We are exploring the depth of the oceans through robots in environments that are not friendly for humans. And finally, medicine and elder care. We have in the Western societies a growingly elder population, and being able to assist them and help them to have a good quality of life is going to be, for achieve this goal, is going to be crucial to have robots that can actually be useful. And if we look at what's the state of the art of robotics, this is a video from 2015 from the DARPA Challenge. These were a dozen of the best robotic teams in the world that spent 2 or 3 years and with a team of up to 100 people working on having robots going through some sort of path and doing simple tasks, what as a humans we would consider simple tasks like opening doors and closing valves and things like this. And what you can see from this video is that although these are the best of sort of human technology and engineering, they are fundamentally stupid. And they fundamentally fail in ways that are, again, stupid from a human point of view. If you think of a 3-year-old kid, my son would never fail in such a way. It's qualitatively different from what we understand as intelligent behavior. And really part of this is the fact that all of these robots during this challenge were either teleoperated or were basically scripted to do a number of operations. So they don't have the capability of adapting to the environment around them. And so very naturally rise the question of what are we missing? What do we need in order to be able to have robots that can interact in sort of an unstructured environment like a house, in a way that is meaningful and safe for the people that they are interacting with. And of course, this is a very sort of complicated question with a sort of difficult answer. But from my perspective as a machine learning person, I would certainly argue that machine learning needs to play an important role in providing robots with a little bit more intelligence and more adaptation capabilities. And in my personal research, I've been identifying different challenges that really are sort of vertically anywhere between hardware development for robots all the way to software and control scheme that we can use to provide adaptation. But the three topics that I've been working mostly in the last 2 years are points like multimodal sensing. How can we give robots better sensing? How can we optimize hardware design? And how can we adapt quickly to new tasks that we have not seen before? And the answer to this are different lines of research. But the one that I'll be talking today, including model-based reinforcement learning for quick adaptation, morphological adaptation for hardware design, and touch sensing. And touch sensing is what I'm going to be focusing today on. So let me dive into this. And I want to spend a word on sort of telling you why touch is so important. Touch is a crucial sensor modality in humans. We use it extensively, often barely even realizing it, how much we really use it. In the moment when you're balancing an object between your fingers, although you don't realize it, you are actually computing forces, and you are balancing these forces so that the object is not falling down. If you wake up in the middle of the night and you look for your phone in the darkness, you are, with your touch, you are at the same time mapping and localizing your phone on your nightstand. And very interesting, people can be born blind, deaf, but we don't have any medical case of people that is born without sense of touch in medical history. And the reason is because touch is really so deeply ingrained into our brain and into sort of our evolution, being the first sense that evolved throughout history. And this is fairly well known that touch is important if you look at the work in physiology. So this is a video from Ronald Johansson, where they would ask people to light a match or do simple manipulation, and then they would remove their sense of touch by anesthetizing while they keep their motor control capabilities. And what we can see is that a simple task suddenly becomes much harder and takes much longer to be solved, exactly because people do rely on touch and use it in order to do this type of manipulations every day. So what's the point of, why are we not having every robot on the planet having touch? And the answer is that touch is and has been historically a hard problem to solve. And there are several reasons. One of the main reasons is that touch is intrinsically an interdisciplinary field, which really needs to be integrated vertically all the way from hardware development to processing of touch readings that you get, to integration into control scheme, and ultimately applications where you can use touch and benefit from touch. And as you can imagine, this is extremely challenging for a single lab to be done, because it requires a very broad spectrum of expertise that might not be available. And what this resulted in is that people have been building and developing solutions ad hoc for very specific problems. And there are probably thousands or tens of thousands of tactile sensing solutions that have been built during PhD by students. And they would build a prototype, they would use it during their PhD, and at the end of the PhD, they would just shelve it, and nobody else was going to use it ever again. And this means that we are basically not having any reusability of the existing components, and people keep building and building the same thing all over again. And of course, this is not the way that science progress. It's not the way that we can build and leverage others people's research. And as a result, we have this extremely high entrance bar if you want to do research in tactile sensing, because before you can even start, you need to first learn how to build your own sensor, which it's going to take you half of your PhD or your whole PhD. So some of the important questions that we've been trying to address over the last few years are how can we lower the entrance bar into the research field? How can we improve reproducibility? And most importantly, how can we accelerate research by enabling the reusability of components so that people can build on top of others' researchers' work? And not surprisingly, the answer that we believe we should give to these questions is standardization. The fact that we need to have common interface and common standards so that we can create an ecosystem of tools that can be leveraged and exploited by researchers for doing their own research. And today, most of the talk will be basically describing the ecosystem of tools for tactile sensing research that we've been developing at MedAI. So one way that I like to think about tactile sensing is by giving an historical comparison against other sensory modalities. And I think that this is really helpful to frame what is the opportunity here and what is also some of the interesting aspects of being able to do touch sensing today. So the way that I like to think about it is by looking at the introduction of telephone at scale for the first time at the end of the 19th century. By having cheap hardware that was widely available, for the first time it was possible to record audio, transfer it over long distances, and play it back on the other side of the world. And this essentially brought a number of very useful applications to our society, but also enabled the creation of a field of computational science dedicated to the understanding of audio, the essentially, digitalization, which at the time was analog, but essentially the study of audio and how can we record it and play it back. And of course, this more recently led also to field of machine learning dedicated to audio, things like natural language processing, which are fields that are extremely successful and widely used into our society. And a similar trend happened in the 90s with the introduction of, for the first time, of cheap, reliable cameras, digital sensors, where now everybody has in our pockets a cell phone with a camera, and we are able to just digitize an image, transfer it over internet, and playing it back or showing it on the other side of the world. And again, this led to the creation of fields of computational science dedicated to understanding of vision as a sensor modality. Fields like computer vision, which again have been extremely successful in being able to understand and make sense of touch, of vision through machine learning. And what I'm here proposing is that we are now at the point where we are starting to have tactile sensors which are cheap and producible at scale. And this will inevitably lead to the creation of a field of computational science dedicated to making sense of touch, digitizing touch, and transferring and replaying at the end. And this field, which we like to call touch processing, I believe will be as successful as computer vision or natural language processing, hopefully 10 years down the line, and really will be focused on making sense of touch as a sensor modality. Now, this will also, of course, open a number of opportunities for research. And some of the fields that we specific pillars that we've been identifying, which we believe are particularly important in order to make touch sensing practical in the real world, are these four pillars: hardware, touch processing, simulation, and benchmark and datasets. And this will be the rough structure of the rest of the talk today. And in addition to this, I will spend one word about applications of touch into our society and building a community of touch sensing across the different disciplines and from different perspectives of researchers that comes to this field. So let's start from hardware. As I mentioned briefly before, throughout the history of touch sensing as a field, we have had many sensors that have been developed in the literature. However, most of them really have stayed at the stage of prototypes. And nowadays, there are only a handful of commercial products that can be bought in the market, while most of the prototypes are just taking dust somewhere in our universe. And when we look at tactile sensors, there are several important factors that we need to consider when we want to use them in a particular application. Some of these factors are availability, of course, cost. The cost of tactile sensor can be very wide spectrum. The form factor, do we care about fingertips? Do we want to have large patches of skin throughout the kinematic structure of the robot? Do we want to have some very specific form factor for our problem? Capabilities, what are our tactile sensoring measures? Are they measuring forces? Are they measuring temperature, vibrations? And with what, how do we quantify this? What is the equivalent of a spatial resolution or force sensitivity? And finally, reliability. Humans, we have amazing hardware because even if we cut our fingers, it will grow back. The skin will heal. But for robots, we don't yet have this type of technologies. So our sensor need to be intrinsically reliable and robust because unlike vision, which is kind of a passive sense where you just look at things, touch is instead active. Every time that we are probing something with a tactile sensor, we are effectively wearing and tearing the sensor itself. So we need to make sure that our sensor is able to withstand hundreds of thousands or millions of interactions. And in the moment when it wears out, we ideally would like to be able to degrade softly and be able to replace whatever interface we have to the world and keep probing by reusing the sensor as much as possible. So as a small, one of the technologies that we've been adopting at Meta and that I personally am a big fan of is vision-based tactile sensors. I believe that Wenzen was here last week, so you probably already know, but I'll repeat it just for completeness. The idea is very simple, was already proposed in the 80s by several researchers. But the idea is that you essentially have an elastomer, which can be, you can think of it as in terms of a piece of silicon. And then you have structured light, typically RGB LEDs that comes and creates shadows and light patterns onto this elastomer. And then you have a camera underneath, which look at this at these patterns. And whenever there is a contact, this contact will create changes in color cues or position of the markers, and the camera will essentially record it. Now, this is really neat because this type of technology does not really have any moving parts beyond the silicon. And because of the wide availability of camera sensors into our markets, it's actually very cheap to produce this type of sensors, and they are fairly reliable and easy to mass produce. So this is actually really cool. The first time I saw vision-based tactile sensor, I was blown away compared to resistive or capacitive technologies. Extremely high resolution, very simple, but also very reliable. And as a small step toward sort of making tactile sensors that are, again, reliable, easy to use, in 2020, we designed an open source Digit, where Digit is the first miniaturized vision-based tactile sensor. It's designed to be extremely easy to produce. It can be 3D printed at home. It's open source, so anybody can actually download it, 3D print it, order the electronics online. And at the end of the day, it's a very simple USB 2 interface. So interfacing this to a computer takes seconds. You just connect it. It's a webcam, bam. You can directly start using it. And really the idea was to have a sensor which is cheap and that can be used as a starting of a democratization process in tactile sensors so that anybody can just get one, build one, and start working on such things. And these are the type of measurements that you would get from this type of device. This is a piece of Velcro, and you can see here the individual key of the Velcro. This is an electronic board. You can see, I don't know how well, but you can see sort of the geometrical structure of what you're touching. And Digit has a special resolution of about 15 to 20 micron. So this is very, very good special resolution. If you would touch your hair, you can either easily see the individual strain of your hair, fingertips. And this is pretty cool, to be honest. So if we compare Digit to the leading tactile sensor available commercially, which is the Biotech, both of them are sufficiently compact that they can be mounted on multi-finger hands. But the Biotech has 29 pixels, while Digit has over 300,000. This is 3 orders of magnitude more. And the cost of buying a Biotech is about $15,000, while the cost of materials for Digit is about 15. So this is 3 orders of magnitude cheaper. And of course, the cool part is that, again, it's open source. So anybody can go to digit.ml, download all the schematics. And if you have a bit of practicality with 3D printing and electronics, you can assemble one, which is pretty neat. Now, over the last 2 years, we've seen over 20 universities replicating our Digit design and adopting it in their research. But the really cool part was that last year, we partnered with JetSite Inc. to actually commercialize Digit. And now everybody can just go to their website. We essentially gifted the right to JetSite to produce this sensor. So anybody can go to the website of JetSite and can order one online. And as a result, this has significantly lower than entry bar for anybody who wants to start using tactile sensing, because you don't need to even know how to 3D print. You can just order it online, get it at home. And in the last year, they've sold over 1,000 of Digit, which makes it the most widely available tactile sensor in robotics. And very recently, Mitsubishi essentially announced that the Digit is now part of their ecosystem, industrial ecosystem. We also have been talking with many other companies and partners really to make it a sort of standard tool that anybody can use as easily as possible. And here there is one. I'll pass it at the end of the talk.
It's interesting they sell it for
$300. As I said, we don't have any control over their price. They make their own commercial decisions. Yeah, we don't get any money out of this. So from Facebook point of view, open sourcing, it was, we actually lose money because of all the R&D. So simulation. Once we have hardware, simulating this hardware is important. Simulation is really a foundational role in science because allow us to quickly prototype debugging and benchmarking advances in robotics. But the problem with simulating vision-based tactile sensors is that traditional rigid body dynamics physics engines are not really designed to do this. And the main reason is because every time that you include a new contact sensor, this is making the simulator basically slower and slower because more equations needs to be solved. And most simulators would basically break after about 1,000 contact points because it would just become slower than real time. And now If you remember, a digit has about 300,000. So simulating a digit would be extremely slow with traditional rigid body dynamics simulation. So what we did a couple of years ago was to design and open source a fast simulator of vision-based tactile sensors, where through some nice trick that I will describe later, we are able to now simulate this type of sensors at hundreds of frames per second, which is fast enough that we can actually do research and use it as a tool to investigate integration into robotics control and so on. And the nice part about this simulator, which we call tactile, is that it's agnostic to the actual physics engines that you use. You can in theory plug it into any physics engine of your choice, whether it's a rigid body or in theory something flexible. And at the same time, it's designed to accept sensor configuration files where you can specify your own files. Of course, it comes with some default systems like digit, but in theory, it can replicate any vision-based tactile sensor that you can design. And for example, here there is a OmniTac, which is a sensor with 5 cameras, and here is it's a Allegro hand with 4-digit sensors. And this is very fast. We actually use it for prototyping, we use it for learning control policies. And in terms of perceptual output, the simulator is actually fairly accurate. So on the top row, you can see different objects simulated, and at the bottom you would see the reading from a real sensor with the same geometry, and it's qualitatively pretty good. It can be calibrated with respect to a specific sensor, and although it's not good at simulating the dynamics because it's using the rigid body engine that you selected, from a perceptual point of view, it's really pretty okay. For be running at hundreds of times. Now, one of the cool experiments that we did using this simulator is actually to do sim to real. And it turns out that by using the simulator, we can learn things in simulation and then port them to the real world. And this works. It helps us to learn faster. And if we then also add a few data from the real world, this is significantly outperforming something that is learned only using real data or only using simulation, which is kind of neat. It really shows that simulation is a useful tool, and sort of it's also coherent with current trends in sim to real and sort of in the robotics. So after hardware and simulation, we still need to make sense of touch. We need to be able to process the data and understand what's happening. And as I mentioned before, we are at this very interesting historical moment where there is not yet a field of touch processing. In fact, there is extremely limited literature on how to process touch sensing, especially high-dimensional sensing. But at the same time, there are very relevant questions that will need to be answered in the coming years. Things like, what are good features for touch? What are the useful structure and computational models that you can exploit? Think, for example, what is the equivalent of a convolutional neural network for touch? Something that can exploit both the spatial, but also the temporal structure, possibly the local structure of touch. So there are a lot of really interesting questions that we'll have to answer to create this science of touch processing. And as a small step toward enabling research in touch processing, we also open source PyTouch, which is the first machine learning library explicitly dedicated to touch processing. And the idea is that we want to be able to provide general purpose interfaces where anybody can connect a sensor to our sort of framework, and then they can use this framework for easily training and comparing models and essentially avoiding all type of boilerplate code. A little bit, if you want, we want to create the equivalent of OpenCV for touch, where even people that are not experts in machine learning can directly download this framework, connect it to the sensor, and very, very quickly get started. And an important part of this is the fact that PyTouch comes with pre-trained models. So in some cases, it's as easy as running 3 lines of code here, for example, for having a touch detector, where we define what is the sensor that we want to get data from. We define what is the task, for example, detecting touch, and then we directly query what is, essentially what am I touching, and is the sensor actually touching? And what's happening in the background is that PyTouch is actually looking online if there is a pre-trained model for that sensor that does this particular task. And if there is, it's automatically downloaded and used automatically. Or of course, you can specify your own model, train your own models using the same framework. And one of the cool experiments that we did at the time was that we showed that we can train features across different sensors, vision-based tactile sensors, for example, digit, omniTac, and JetSci. And the features that we learn can actually be used for pre-training on new sensors. And this is actually beneficial in terms of performance by compared to just using data from one particular sensor. And this is already aiming at the fact that it's very likely that we can learn general purpose touch representations, and that this representation can help and be useful in the same way that, for example, ImageNet features are useful in vision. More recently, we also had a very interesting work on learning reducible visual tactile representation, where we essentially learn this visual tactile representation in a self-supervised manner without knowing what's the sort of downstream task. And then we can actually apply it to several different tasks, including active control, and show that the performance of this self-supervised representation is actually useful and improving performance, which again feed into this sort of line of work of studying, what are the right representation for touch? How can we learn representations that are generalizable and useful, and so on. So once we, go over touch processing, the last of the 4 pillars is benchmarks and datasets. Benchmark and datasets are at the core of our work as a scientist. Benchmarks are, of course, super important to measure progress into a scientific field, and datasets are very useful to enable, standardization and proper, collaboration also within the scientific field. And both of these have been sorely lacking in touch sensing. Mostly because of the lack of standardized hardware so far and the lack of simulators that would enable them. But recently, thanks to tactile as a simulator and digit as a hardware, we are now, or we should really be able to start discussing about, as a community, what are the benchmarks that we care about? What are the benchmarks that we want to put in place to measure progress? And how can we generate larger and larger data sets that can be used by researchers that don't necessarily have access also to hardware? And I think this is a discussion that we need to have as a community rather than being imposed sort of from the top. And as a very small step with our tactile papers, we also provided essentially a small data set of 1 million grasp on a simulator of a single object. And this was, the task is trivial, but this is interesting because for the first time, we can train models at a scale which is 2 orders of magnitude larger than the previous data set collected on the real world. And by doing so, we can start looking at how some of these models work at a scale that was previously impossible to test. And I believe that this is going to be very important, especially with the current trends in machine learning of having larger and larger models. So finally, I want to spend a minute about applications. As I mentioned before, I very strongly believe that touch will have a lot of useful applications into our society. And here there are a few of them that I'm personally sort of interested or keen on. The first one is prosthesis. There is obviously a very obvious interest in being able to provide people that lost their limbs in being able to sense again and touching again, both from a emotional point of view and from a functional point of view. If we can give them better grasping, better sense of their feet or hands, of course, this is absolutely worth. Another application is the metaverse, and I will spend a word on this later. E-commerce is also a field where I believe that touch sensing can provide very interesting results. In the same way that we currently are able to do visual queries, where you take a picture of an object and say, hey, buy me these things online. I believe that at some point in the future, we'll be able to do tactile queries, where you touch a sweater and say, hey, buy me something that has the same texture or that is as soft or with the same material as what I'm actually touching. And finally, robots. Of course, I'm a robotician in my heart. So I believe that agricultural robotics, medical robotics, service robotics, they would all benefit from having touch as sensor modality. And I really hope that 5 years down the line, every robot that we build in the world should have a tactile sensor. So about specifically metaverse, I want you to think about the fact that touch is actually the deepest social and emotional sense. There is nothing like hugging or touching a loved one from an emotional point of view. And if we are able to digitize touch, transfer it over long distances, and replay it, I really believe that this would be helpful in being able to communicate better this sense of emotional sense of touch and being close to your loved one. And of course, this introduces challenges, technical challenges on how can we sense, calibrate, and reproduce touch over the distance in the same way that we can do it with audio, for example. And of course, also very interesting, how can we accurately and easily digitize objects and their physical properties like friction, weight, and so on, using tactile sensors into virtual worlds. And generally speaking, my work is in these two parts of sensing and processing touch. I don't know how to reproduce touch. This is up to optics people. This is a fun sort of papers that we had a few years ago, where the idea was that we had robots with tactile sensors, very simple capacitive technology. And we also had an optic lab that would simulate sense of touch through vibration motors. And through flex sensing, we were able to control the hand of the robot. And this system was used in conjunction with an iCap humanoid robot, VR Oculus Rift SDK kit, where people could essentially see through the eyes of the robot, could move their head and control naturally the eyes and the neck of the robot. And then there was a Kinect that was able to infer the kinematics structure of the operator and project it onto the robot's control. And I like to show this video because recently, just a couple of days ago, there was the NAA X Prize of teleoperations, where they can actually make people feel like they are into a robot and control them remotely amazingly. But this work was one of the very first to actually show natural teleoperation of humanoid robots almost a decade ago. And I sort of like to show it. And it actually worked. And touch was actually pretty important. Without touch, operators were not really able to even grasp objects because it was hard to know what was happening in terms of interactions. Finally, robot learning. As you might imagine, we've been working on a lot of different aspects of machine learning, for learning touch, and using touch in robotics. And some of this work over the years include predicting grasp stability, learning how to regrasp and grasp different objects, learning multimodal representations where we can identify objects and their visual appearance from touch, active tactile exploration, and 3D reconstruction from vision and touch, both in passive and in an active manner. But one of the work that I also think are kind of funny, at least I had fun, what we presented it last week, 2 weeks ago, IROS, and it's a paper about using touch for learning how to play piano in simulated environments. And for anybody who play an instrument, you probably already guessed that touch is actually fairly important in order to be able to modulate force and the sound that you want to have and the timing. And we essentially show that by using touch, we can learn better, playing policies. Also in conjunction with the modularity, where we can just give any score, and by dividing into modular policies, we can basically learn how to play it, without any further learning. Finally, another task that I've been very interested in is fine manipulation. I think this is a really hard problem, generally, because vision get occluded. So without vision, if you don't see what you're trying to manipulate, you cannot really. And touch here play a really important role. And one of the tasks that we've been solving a couple of years ago was to manipulate a marble glass between two robotic fingers to specific configurations that we can set. And this is actually very hard because if you apply too little force, the marble will slip between your fingers. And if you apply too much, you will squeeze the marble out. You'll basically shoot it out. So being able to maintain contact, control contact, is actually really difficult for a robot. And the way that we approached this task was to use, of course, our digital tactile sensors in conjunction with a model-based reinforcement learning algorithm that we designed. And the idea was that we would essentially take raw images from our tactile sensors. We would encode them into a latent space through information bottleneck. And then we would learn a forward dynamics model that, given this latent state and candidate action, would predict how the state would look at the next instant of time. And this forward dynamics model, in conjunction with the model predictive control, essentially was able to determine the set of actions to perform in order to go from our current state to our final desired state. And this actually worked fairly well. And now, the missing point that I think we have is that as a humans, we have hands and perception, which enable us to do amazing manipulation. And our robots today are still very, very far away from this. But I think that, with better hardware and through the use of tactile sensing, my hope is that we will ultimately get there. I want to have robots that are able to, juggle and manipulate dough, as somebody was saying. And, I think this is a really cool challenge. And as a small step toward doing this, I actually, I get a lot, do we really need touch in order to be able to, manipulate objects? And my natural answer, sort of instinctive answer is, yes, I strongly believe that we do need touch. But we recently also showed that this is not necessarily the case. Kind of funnily, we showed that it's possible to learn in simulation and then transfer to real robots policies that don't need vision, don't need touch. This robot learn how to manipulate all of these objects purely from prior perceptive information, just from joint, position, and velocity. And this is working extremely well. In fact, we originally wanted just to create a baseline to show that touch is useful, but this works so well that it actually had to be published on its own because it's amazing. I was mind blown. So do we really need touch? My answer is still, I believe we do, but I cannot conclusively prove it for manipulation. There are proofs in the literature that it's actually useful for learning how to grasp or learning how to do other tasks. But I think that we need still, that one particular killer applications where we can show, look, this you cannot really do it at all if you don't have touch. And I think this is going to be a really important moment that will happen hopefully in the next couple of years that we are able to show this concretely. And as you can see, this is extremely robust. Yeah. The only information is position and velocity of the joints, nothing else. Yes.
Nothing about it.
Nothing at all. The algorithm is actually inferring properties about the object in sort of an online estimation way, but nothing is provided to the algorithms at deployment time. The algorithm has no idea what it's rotating.
Roberto, did you have to build in any kind of compliant controller in this at all, or was it just kind of the natural compliance of the Allegro hand?
It's the natural compliance of the PID controller of the Allegro hand,
yeah.
But we didn't tune anything. Okay. This is just out of the box, basically.
Yeah, from a question online, is this about achieving the level of fine manipulation units that how much of that comes from sensing and how much of that is comes from the fineness of the actuation, robot actuators versus humans?
That's a very good question. The answer is that I don't think I don't know. Maybe somebody else on the planet knows. Going back to the video from physiology from Ronald Johansson, I do think that in humans clearly touch plays an important role, but again, it's hard to quantify, I believe. So to conclude the talk, if you're interested in tactile sensing, there is an online community at www.touchsensing.org. This leads directly to a Slack channel, which has over 200 researchers in the field that use this Slack channel to communicate, share results, papers. If you have cool papers that you publish, you should post it there so that other people have visibility into it. And this is, unrelated to Meta. It's completely for free. It's run basically by volunteers. And I also want to thank all the human collaborators I had throughout the years. I'm honored to have worked with such amazing researchers. And all of the work that I've shown today would have not been possible without them, including here our Dinesh. I'm very flattered to work with all of these cool and really nice people. And so to conclude, I hope that today I convinced you that touch is a key sensor modalities, both for humans and robots. And during the talk, I presented the ecosystem that we've been developing over the years, and in particular, our hardware tactile sensor digit, our simulator tactile, and our touch processing framework, PyTouch. Really with the idea that we want to investigate more and more into the nature of touch as a sensing modality. We want to be able to make sense of touch and use it to better understand the scene and control our robots. And the long-term goal is really making touch sensing practical and useful in the real world beyond just research labs. And sort of, my final pitch is that I believe that now we are a very crucial moment in history where we are at the verge of basically a digital revolution of touch, in the same way that I already mentioned revolutions in audio and vision. And hopefully this will make touch sensing more available and ubiquitous into our societies and enable new interesting applications in that will be beneficial. So thank you very much, and I'm happy to take questions.
I have a quick question about the tactile simulator.
Yeah.
So you mentioned that it's not quite there in terms of the dynamics because of the bodies. I'm just curious, like how do you approximate like the gel dynamics? You just use the rigid body simulator, but you just tune the like contact stiffness to be very, very low, and you could say that's somewhat how the gel like interacts with objects, or there's something more sophisticated going on.
Yes. So let me. So first of all, your phrasing implied the fact that tactile is not accurate in modeling the dynamics, while really we are piggybacking on whatever physics engines we decide to use. And yes, virtually every physics engine available on this moment on the planet sucks at modeling contacts. But this is not a limitation of tactile as a piece of software. It's a limitation of our understanding of physics and how to model contacts. Sure. We do model, essentially, the simulator has a transfer function for the gel. So every time that you apply, you give a geometry and an amount of force, what's happening in the hood, under the hood, is that the simulator is transferring how much this geometry would actually be compenetrating the silicon. And based on this is then generating all the lighting using OpenGL. So the actual perceptual part is pretty accurate. We also simulate the pixel noise of the sensor of the camera. If you have this information, we do have this information for digit. We do not at the moment incorporate the sort of the low pass filter dynamics of the gel. Typically it's a Gaussian, but it's fairly easy to add if you want. In practice, it doesn't make a big difference. We'll see.
I mean, Wenjin last week, she talked about something that the gel suit was quite capable of doing, which seems like an important feature, which is like during incipience, you get something quite subtle, and that like the contact time starts to decrease. Yeah, is that something that TACO can simulate, or I'm guessing no?
I don't think that any physics engine can simulate incident sleep. If the physics engine can tell you that there is a decrease in the force that is being applied, TACO can simulate it. But I don't think that the physics engine can. I would also like to specify that incipient sleep, vision-based is not the best mode to detect incipient sleep. Humans use vibrations to detect incipient sleep.
Can you explain what that is?
Oh yeah, incipient sleep is the fact that when something is going to sleep between your fingers, as a human, we are able to detect this before it actually happened, about 200 milliseconds before. And the way that we do it is, well, I guess it's kind of magical, but is that we look at vibrations and we realize, okay, this thing is actually soon gonna start to move before it happens, which is kind of really cool.
Yeah, the fact is before it actually happens is
yes.
So you made this really important point, I think, early on about how the growth of sensing as a commodity in these other domains like vision and audio was really closely tied to the growth of playback as a commodity. Right?
Yep.
Like vision was tied to the fact that we have televisions and we have other playback devices for camera sensing. And similarly, audio, I mean, even from the beginning, we're able to play back. Right? The touch, maybe that connection between the tactile sensing community and the haptic community seems like it's not as much there. It feels kind of important to build that, right? Like it feels like almost both kind of commercially and also in terms of even figuring out what are the tasks that a good tactile sensor should solve. It seems important to ground it in what does a human feel like when these sensations are played back to them, and does it feel real? That feels like, it feels like the smell test, the touch test that tactile sensors pass.
Yes. I agree. I think that, yeah, historically, the two communities have been a bit disjoint. I think that another part of the problem is that the haptic technologies that we have at the moment are not quite there yet either. It's very hard to simulate accurately touch. It's kind of primitive what you can do at the moment. I would argue that there is in theory another way of how touch could be useful, which is by essentially directly comparing digital touch. Even if I cannot replace it, reproduce it, in this moment I can compare two readings, and with the right features, I can determine if the two things match, for example, or how different they are. Yeah. But I agree that ideally we would like to be able to replicate touch. I think it would give us also a better insight into the features that we want to learn. If you can physically sense it, then it's very obvious, no, this doesn't feel right. Yeah. We need more data, we need more information, so we need better features. Yeah. But yeah, I don't do any work on optics.
Yeah.
It's outside of my field.
Yeah, but I feel like maybe we should. I mean, those of us who are interested in touch, we should try to get somebody to try to play back some signal starting from one of our favorite sensors. Let's say we take digit, and we try to get them to play back something to a person and see what it feels like. Through that process, in that closed loop, somehow improvements will come to both the playback side and the sensing side.
My sense is that our sensing technology is probably order of magnitude more accurate of what can be played back at this moment. But
so another thing that maybe I can ask another question, I'm not holding anyone else up. I think the point that you were making towards the end about we don't really know whether touch is in fact necessary for manipulation. Perhaps another way to think about it is that touch should be treated at least as privileged information during manipulation. That it will enable you to, meaning during the learning of a manipulation task, it's a privileged information that will enable you to learn much faster. So one very intuitive way to think of it is that touch will enable identifying key moments during the learning. Like, for example, that you did something bad and you felt pain by contacting something sharp, or that even just the fact that you got into contact with an object feels like an important, and at what point of the object, that feels like an important, easily identifiable signal that touch provides to you, which is maybe not as easily available through other means. But more broadly, right? I mean, during the learning stages, you're dealing with more erratic policies and a wider distribution of sensed states. And it feels important to have as many different views of that basic underlying state as possible, from vision, touch, everything, until the point at which you figured out that this is the right thing to do. Maybe at that point, it's enough for you to just act from vision, right? Maybe at that point, you already know that the manifold of states is small enough that you can, each visual percept actually maps to a unique tactile percept, and you don't really need to keep the tactile percept in.
Yep. I was looking for a slide, which I thought I had a backup slide, but I actually don't. I completely agree. I think that there are, the difference between having a finger touching something and not touching it is a matter of, millimeters, microns in some cases. And from vision, it's virtually impossible sometimes to distinguish. But if you have a tactile sensor, you have such a clear signal that you're actually touching or not, that it really helps you to disambiguate. A lot of times, the way that I think about touch sensing is that it's a sense that reduces uncertainty better than other sensing modalities that we have. Certainly better than vision, certainly better than force torque sensors, as we were discussing over lunch. And being able to sense and shrink this uncertainty in control can be very valuable. Another argument for why you might want to use touch as a privileged information is the whole argument that the concept of force is not necessarily an obvious concept if you just look at the state through vision. While if you use touch as a privileged information at training time, you are able to identify the fact that such things as force exist, the concept. And even if you are no longer able to sense forces later on, just the fact that you might have this concept might actually be helpful in the first place. Now, this is an hypothesis. I don't have proof to show this, but I think it's fairly reasonable and likely that this is going to be the case. If you know that something exists, even if you cannot measure it, you will still keep it in mind and use this information, potentially trying to infer that information from other factors.